So today the problem that we're going to explain or that I'm going to explain is minimum number of removals to make mountain array. So basically what we have to do is we have an array and then we have to remove some elements from the array such that there is an index I which satisfies this, right? So for basically on the left side of I including I everything has to be increasing, and on the right side of I including I everything has to be decreasing, right? So basically it's called a mountain array. A mountain array is an array which first is increasing and then is decreasing, or to be more precise, first is strictly increasing and then is strictly decreasing, because you can see there is no equality. So it's strictly it has to be increasing or decreasing, right? So let me show you some diagrams, and that will help to clarify this question even further. So suppose I have taken this example, this array example, which I have here, and then what can we do to make this array a mountain array? We can remove basically gas this element, and this element can be removed, right? And as well as this element. So all these elements are removed here, and we can see the resultant array is first increasing and then decreasing, right? So it becomes a mountain array. Now that we have this information about what the question demands from us, now let us look at some intuition. So if you look at this particular 6 here, so this on the left side is nothing but the longest increasing subsequence ending with 6, right? And on the right side is nothing but the longest decreasing subsequence starting from 6, right? So uh, and why is it a subsequence? Because the elements don't have to be uh, in a subarray, right? They can be separated out, or there can be elements in between. But if you for example, if you look at this subsequence 631, so this comprises of 6 and 3 and 1. So it doesn't include 2, but that is the definition of subsequence. We can skip elements in between so as to retain our property, right? So that's the entire idea. What we'll do is that we'll go through each and every I or index of the array, and then try to identify the longest increasing subsequence on the left hand side which includes it, and on the longest decreasing subsequence on the right hand side which includes it, right? That is what we're trying to identify here, and then we'll be able to solve the problem. Now this is a pictorial description of an algorithm. Suppose we choose I to be 2, right? So now I is here, I index of I is 2, I is at 1. The longest increasing subsequence on the ending at 1 is basically 1 itself, because you can see on this side there is nothing that you can take to increase the length, right? So it's only 1. And similarly on the right hand side, the longest decreasing subsequence including 1 or starting from 1 is basically again 1 itself. So if we add the lengths of those up, right, we'll get 1 plus 1 is equal to 2. We'll get 1 plus 1 is equal to 2, and obviously we need to subtract this, because this is the common element. So basically we get a length of 1. That this is our length of the mountain array. We identify the length of the mountain array, and the elements to be subtracted are basically the entire length of the array minus this length, right? So that is what we need to subtract. So here it is basically we are only subtracting one element, so this is definitely not the optimal solution. If you look at if the I is placed at 5, then the if you look at the green boxes, then they comprise of the longest increasing subsequence ending at 5. And if you look at the red boxes, they comprise of the longest decreasing subsequence starting from 5, right? So again, if you add them up, it will be 2 plus 3 minus 1. again 4. So that means you have to remove how many elements? The length is total length of the array is 1 2 3 4 5 6 7 8. So 8 minus length of the mountain array is the number of elements you have to remove. So 4 elements you have to remove. In this case you have to remove 8 minus 1 equal to 7 elements you have to remove. So this case is better than the earlier case, but I think the best case scenario would be if you would have placed. Is there possibility to create something better than this? I think there is not, because if you had chosen I to be 6, then also I think you would get 4. But you basically got the idea, right? What you are trying to do here. So we are basically will iterate I over the entire array, right? And then we'll try to find a valid try to figure out the length of the mountain array such that we have to deduct we have to like remove the minimum number of elements. That means we have to find the maximum length of the of such mountain array, and it has to be a valid mountain array. That means that there has to be the subsequence has to be at least one. I mean, the increasing subsequence has to be at least 2 length, and the decreasing subsequence has to be at least 2 length. That means this is one of the simplest mountain array, valid mountain array that we can find, right? 5 2 3. So this is a valid mountain array. This you can also say that this is a mountain array, but this for this problem we'll treat as invalid. It has to be the length of the increasing subsequence has to be 2, at least 2, and the decreasing subsequence also has to be 2, right? So that is what we have here. So now let's look at the code, how we are going to solve the code. So here we basically take the vector which is the input, right, which is the in starting array, and then we try to find the longest increasing subsequence for every index of the array, right, ending at that index, right? So for example, we basically go from I equal to 1 to I equal to n for the index, and try to populate the longest everything is populated as 1 by default here. This LIS and LDS arrays which capture the longest increasing subsequence ending at I and the longest decreasing subsequence starting at I, right? These two those are obviously initialized as 1 because the worst case scenario can be 1, the whole element itself, like this scenario, right, which I already showed, this particular scenario. Now what we're trying to do, this is the basic LIS ending at I code. So basically when we go from I equal to 1 to I equal to n, right? These were the LIS. So uh, I equal to 0 doesn't make any sense because there is nothing to the left of it. So there is nothing to see its value will always be 1. So we start from I equal to 1, and then j goes till before I, and then if num psi greater than num j, then we obviously uh, we can the value of the longest increasing subsequence will be longest increasing subsequence ending at j plus 1, because I is an additional element now we have found which is greater than j, so that can be included. So this is what the formula comes from. We'll do this for all j's and take the max. That will be the longest length of the longest increasing subsequence ending at I index, right? And after that there is some trick that I've performed. So I could also write a similar code for the longest decreasing subsequence, but that would be repeated code. I don't need to do that. So what I've done is basically I've reversed the number. This is a trick. I have reversed the number and then taken the populated the LIS and again reversed it, right? This will give you the LDS. Okay, you can think about it for a while. So I think probably I can explain. So suppose this is a simple array, right? The LDS at 3 will be 2. LDS here will be 2, right? No, pardon me, I have taken the wrong example. Let's take this example. LDS of this position will be 2 because this sorry will be 3 because this includes this and this. So the length of the longest decreasing subsequence starting at this particular index of I equal to 0 will be 3, right? But I don't want to write a separate code for this. I want to use by length of the longest increasing subsequence. So if I reverse this and calculate the longest increasing subsequence, I'll get the longest increasing subsequence at here will be 3, because longest increasing subsequence is length of the length of the longest increasing subsequence ending at 3, right? I mean, that will be 3, and then we have already written the code for that. And if we reverse it again, so now if you look at the LIS array here, this will be 2 at this index, and at this index it will be 1. And then if I look at the LDS array here, at this index we'll get 2, and at this index we'll get 1. And if we reverse this solution that we found from the LIS function, then we get 3 to 1, which is basically what we want, right? The LDS function to populate. So this trick, first you reverse the nums and then you reverse the answer itself, will be effectively give you the LIS array. I mean, at every index we'll get the length of the largest length of the longest increasing subsequence ending at that index, and then use that code to calculate LDS by this short trick, right? Let me reiterate further. If you use the code for the LIS to find the LDS by first reversing the nums and then reversing the answer. Okay. So these are some print statements which you don't really need. So let me remove them. And then obviously, what is the minimum number of renewables? You go through every index and then make sure that the I mean, you have this criteria that is the increasing subsequence should be at least of 2 length, and the decreasing subsequence on the right side of the peak element should be at least of 2 length. That is our criteria, right? And then the minimum number of elements would be n minus, like, the length of the longest increasing subsequence ending at I, length of the longest decreasing subsequence starting at I, and obviously I, because I comes twice, so we have to add it. It's simple Venn diagram strategy, right? And then that's how you get the min removals. And then for every I, whatever minimum value you can get here, that will becomes an answer, because we want to remove the minimum number of removals, remove the minimum number of elements, because that's the requirement of the problem, and then we return it, right? So okay, that's about this question. I think it's pretty easy enough, right? Especially this trick makes it even more easier, and I mean, at least more sleek code wise. This is preventing you from writing a lot of extra code which you never want, right? Uh, and then okay, so I think that's it. I'll see you in the next video. Thank you.